Hi, I'm Professor Alan Duffy, an astronomer from Swinburne and the co-founder of MDetect, a company that builds muon detectors for use in scanning through the Earth and exploring the highest energy side of our universe. And that's exactly the experiment that you can try to do today using some of our educational detectors. Now, before we delve into that high energy universe, to set the scene a little bit, this is an object that I hope is familiar to some, but maybe not in this exact shape. This is the galaxy we live in, the Milky Way. It's a flat disk, essentially like a pancake, and we're looking directly along back into the heart of our galaxy. Because it's, well, in a dark night sky, you'll see it stretching out overhead. It's a 3D object, but we're trying to put it onto a single page. This is a problem we have when we try to show the Earth, for example. So this is an example of a mole-wide projection. We do exactly the same, turning the whole structure of our galaxy, wrapping all around us in the night sky, into this nice single flat image. We are looking along the horizontal is the disk of our galaxy, and we're looking right into the galactic center where there are billions of stars all shining brightly. You can also see the small and large Magellanic Clouds just off to the bottom right below the plane of our disk. There's some dust trails. These are the dark regions that are blocking the light. Now, this is visible light, normal light you and I see in. If instead we switch to longer wavelengths of light, radio waves, this is emitted by colder objects. And in this particular instance, it's the dust and gas that lies between the stars. You can see how messy it all is of our galaxy. Just off in those little gaps between the clouds of material, though, there are these little patchwork features. That is the afterglow of the Big Bang, the cosmic microwave background, long since cooled down to these incredibly cold temperatures that radio waves are emitted at. If we go instead to the other end of the spectrum, so from very cold, low energy universe to the highest energy, now seen in X-rays or even gamma rays, we have really different view. Now, again, we see the disk of our galaxy. You can see blobs along it. Those are the explosions of stars known as supernovae, the shock waves of which are ripping out into our galaxy, slamming into the gas and dust and heating it to millions of degrees Celsius or Kelvin, and then they glow brightly in gamma rays. There are also little dots dotted all around the heavens. That is in fact a feeding supermassive black hole sitting at the heart of a galaxy, an object we call a quasar, so bright we can see it across the entire visible universe. Now, it's not just gamma rays that we get shining brightly from exploding stars and feeding black holes. It's also high energy particles that slam into our planet. They collide with the atmosphere of our planet. Thankfully, that is our shield. But in doing so, they also produce a whole zoo of particles that can make it to ground, and in particular, are muons. These are the heavy cousins of electrons. They travel through hundreds of meters of rock, but eventually they do get stopped, and in particular by dense structures. So at MDetect, we place our detectors deep underground and use those incoming muons like X-ray scans. We, under dense regions, will see a shadow where more muons are being absorbed than we had anticipated, and under underdense regions, there are, well, essentially there's a hotspot. There are more muons arriving than our model suggested, telling us that there's in fact a low density region, maybe an air cavity. And that's exactly one of the use cases of muon scanners. It's incredible work that has gone to the Great Pyramids. The teams have placed muon detectors all around within and around the Great Pyramids, and they're looking for hotspots where more muons arrive than they had expected, revealing a hidden burial chamber. Now, as you can see, these muon detectors come in all shapes and sizes and configurations. MDetects are very simple, very refined, based around robust and high-performing plastic scintillators that sit within these blackout cases. We have a camera that sits within, and it detects the flash of light when a muon strikes our plastic scintillator. When we place them above, we then see a muon go through the first layer and the second. Only a muon has the energy to do that, and as quickly as we can search for. So essentially within a microsecond, only the muon can make that kind of trip, and that allows us to detect muons. Those signals then go into the red control box, and that goes into your computer. Now, you can do a range of other kinds of physics with the EduMods. For example, you can explore absorption studies of radiation. And in this fashion, we would put a large block, a lead brick in this picture, or a bit of steel, or even a tub of water in between the two planes. And powerful as those muons are, they will eventually get stopped. And what you will see with one detector with the feature between and perhaps a nearby detector as a baseline, you'll start to see that slowly but surely muons are prevented from hitting the second slab. So they go through the first and then get stopped by your absorber and don't make it to the second. And over the course of about 30 minutes, you can begin to tell the difference and indeed even measure the density of that structure. If you have the muon detectors, though, separated horizontally, and they start to register counts, what you're seeing then is not one muon, but rather a couple or many. That is a shower of muons, and the very highest energy particles will create these showers or bundles of high energy particles that come crashing down. Over the course of an experiment, you can begin to move the detectors apart. You'll see ever fewer muons hitting both at the same time. You are beginning to measure the size of that shower as it comes down, but also you are exploring an even more absurdly energetic side of our universe. Truly, only the most energetic particles, far higher energies than anything we can produce on Earth, are being fired at the planet from these glowing stars or feeding black holes, slamming into our atmosphere and creating these large shower events. Now, inspired by the global cosmic ray network credo, we want to create the Australian Cosmic Ray Network. This will search for cosmic ray showers not over those kinds of meter distances, but rather thousands of kilometers, because Australia has one of the largest contiguous land masses under a single jurisdiction. With detectors in schools and research groups across the country, we can find showers that are as large as nations. The kind of particle that might create that is truly the unknown. So with the EduMod, you can explore both the known sciences, radiation sciences, special relativity, absorption studies, but also explore the unknown and try to search for the highest energy particles that humanity has ever seen, and perhaps even higher than we ever have before as we explore the unknown together.